Sorry, can you hear me?
Yep.
Okay. I'm a cryptographic engineer at the Electric Coin Company, an anarchist. I really care about using cryptography to protect people's individual privacy and the freedom of expression, especially the freedom of expression of minorities. I'm the lead author of the Zcash protocol specification, and I've written papers on, co-authored papers on the Halo proof system and the Sphinx post-quantum signature algorithm.
Izaak?
Hey, so I'm Izaak. I'm CTO at O1 Labs and one of the co-founders of Mina, which is a succinct SNARK-based blockchain. It's a SNARK-based succinct blockchain. Currently, I'm working on Snaps, which is kind of the private smart contracting layer for Mina. And I don't know, I do all across the SNARK stack. Okay.
Nice. Zach?
Hi, everyone. I'm Zach. I'm a cryptography engineer and the CEO of the Aztec protocol. We are a company that builds privacy-preserving solutions for the Ethereum blockchain. So we've recently deployed a private rollup to Ethereum that enables private transactions using recursive ZK snarks, particularly Plonk snarks, which Ariel and I co-authored. And yeah, we're pretty passionate about enabling privacy-preserving private smart contracts on distributed consensus layers.
Jordi?
Hello, I am Jordi Baylina. I'm a communications engineer. Currently, I'm working in the Hermez Daira rollup. It's a layer 2 solution for payments on top of Ethereum using Growth 16. And I'm also the owner of Circom.
And Pratyush?
Hi, everyone. I'm Pratyush. I am a fifth-year PhD student at Berkeley. I am a co-author of many libraries in the Arcworks Snark ecosystem, and I'm also a scientific advisor to Alio, which is a startup that is doing decentralized private computation.
Thank you. And I'm Georgios. I'm a research partner at Paradigm. We're an SF-based crypto venture capital firm, and my work focuses on the crypto of our portfolio companies on the engineering, protocol, and auditing ends. So without further ado, let's get right to it. Firstly, I think we should organize the discussion in some logical segments. So the first one should be around proof systems, then around the security properties of the things that are deployed and how many people are trusting and verifying what's going on. An emerging field around smart contracts written in circuits. And finally, we can talk about the future. So to kick things off, maybe Izaak, you want to take the first question. Why do you think zero knowledge proofs are important technology? And what use cases are you working on?
Okay, I guess interesting question. Well, maybe at the risk of getting a little too philosophical, I would say like okay, stay with me for a second. Okay, okay. So if we were all if we were all able to coordinate our actions perfectly, there would be no use for zero knowledge proofs, right? We would all recognize that, we're one thing, we're all working together. There's no need for hiding things. There's no need for convincing. We understand each other. But that's not the case. And there's, in the universe, pockets of internal coordination, which are sort of, walled off from other ones. Like, inside of this brain, maybe I can mostly trust what's going on, but maybe you over there, you're not so sure about what's going on over here. So, you demand some proof or something. And on the other hand, maybe I'm not so sure about what's going on with you. So I want to hide something about you from you. So, that's what zero knowledge proofs allow you to do, to kind of, I guess, bridge that divide of mutual non-complete understanding. So I would say that's why they're an important technology. It's a very general technology, as we all know. You know, the number of use cases is,
So more on the, let's say, on the privacy end rather than the information compression and the verification end.
Well, no. It's the same. It's the same idea, which is that like you and I are not the same brain, and so we don't. You don't believe everything I tell you necessarily, and I don't want to share everything with you, because we can't coordinate we're not in recognition of our identity with each other. At the risk of getting too philosophical, I said, but
philosophy is good. That's fine.
Okay, but yeah. Anyway, that's why it's important, because it allows us to bridge, maybe in a technological way. You know, there's of course social ways that we can bridge that divide, living in close proximity to each other, building trust, etc. But it's a technological way of maybe bridging that divide. Specific use cases, there are many. You know, they're parameterized by circuits, so programs. You know, so there's very many. But some ones that, you know, I think are kind of interesting and underexplored. Well, okay, so there's the ones everyone knows about, like about compression. You know, for like. You know, for blockchains and that kind of thing, and privacy for, you know, like kind of semi-public computation, like blockchains or payments or stuff like that. Some ones that I think are sort of interesting and underexplored are using them for sort of flexible modes of authentication. I said this kind of recently, but I'll just say it again. Like where maybe you have like a, you know, a dance club for people who only live in, you know, who live in the neighborhood only, or something like that. I don't know. And then also for, I think another kind of interesting use case is sort of for like a durable reputation that you can move across platforms, in a privacy preserving way. But there's a bunch of interesting use cases that I can also, I don't want to monopolize the time. I'll shut up now.
That's great. If anybody else also in the panel has any good thoughts on this, by all means, go ahead. It seems to me that we have, in a way, two groups in the discussion, some that are more focused on the more private payments aspect of it, and some, like, for example, Jordi's group, that are working on more on the compression, and that's what originally prompted the question, whereas Daira's work also is focused more on privacy, is my understanding.
I mean, it's not just private payments, it's private everything, or private everything that you can express in computation or communication. I'd actually say that even if you trust someone implicitly, if you trust them with your life, you still need to be able to keep secrets from them. That's just part of human relations. So, yeah, everyone has the right to privacy.
Or the generalization of proving systems. You can prove things, and with zero knowledge you can prove things, and you can prove. You have more flexibility of what you want to prove. You can prove that you made a computation very good. You can prove that you hold some data without revealing exactly which data. But at the end is this concept of proving, verifying. This is something that's new. You can prove things and people can verify these things. Signature is also a proving system, but it's like very limited. You just prove that you signed a message. But with zero knowledge, you can extend that. You can write a code explaining, so a statement what you want to prove, and this is something that's, I think this opens the number of applications a lot.
Yeah, and also you could make a mistake in sort of communicating a statement. It's not just whether someone trusts you, it's also do they want to rely on you being correct, which even if you're completely honest, you may be incorrect.
Zach, you want to say something?
Yeah, just to add into the conversation, I think that zero knowledge cryptography, particularly the combination of zero knowledge cryptography and blockchains, is a genuine game changer, where, or at least a potential one, where it has the chance to completely revolutionize the way that individuals coordinate with one another and do business with one another. Because at its core, it allows individuals to coordinate with each other in a secure manner without relying on trusted intermediaries. It's very similar to the original ethos of Bitcoin, except now you can do it without revealing information to observers, which makes it, in my opinion, a lot more valuable and lucrative, because you can start to do meaningful, you can start to create meaningful, interesting, innovative financial instruments, syndicated traded settled through a blockchain, without the associated problems that you have with public assets, where everything's visible, where you can get front run, people can analyze your position. You know, if you live in a country with where the rule of law is not particularly strong, then having people know that you own lots of cryptocurrency could be a big problem for you. And I think I think a lot of people obviously got very excited by the possibilities of these kind of new innovative forms of financing. It's one of the reasons why blockchains are so valuable. But I think that privacy is really the missing link required to kind of bridge the gap between where we are now, where blockchains are used heavily by early adopters, technological enthusiasts, and investors, and actually make it something which is viable for the mainstream. And I think that has the ability to enable some profound social good, combined with the ability for innovative startups to really start to disrupt traditional entrenched financial services industries.
Yeah, I'm personally a big fan of having the ability to do private finance in the same way that we're doing DeFi today. Yeah, I guess like zooming.
To be honest, I'm quite ambivalent about this being used for finance. I mean, I would almost abolish money if we could. But if given that we have money, you can't have privacy without financial privacy. I've said it before and I'll say it again.
Right, that seems to be like the obvious use case, let's say. Zooming in a bit more, because like we covered kind of the philosophical angle of this. So there have been lots of proof systems which have been developed and deployed over the years. But I think that everybody has kind of decided or chosen which ones they want to use. So which ones have you people deployed, built on, and what were the criteria for choosing the proof system?
As the most biased person in the room, could I start perhaps?
Absolutely.
Yeah, so we used Plonk because well, yeah, as the inventors of it, we really invented it to solve the problems we were facing with deploying programmable ZK SNARK circuits to a platform like Ethereum, which has quite constrained cryptographic primitives you can work with. So yes, pretty biased. We exclusively use Plonk. We've been making a lot of advancements and upgrades to it over the last 2 years. So now we have create odd things like the ability to have lookup tables inside your SNARK circuits, the ability to create much more like kind of imperative types of programs that represent them as algebraic proofs more efficiently. I guess maybe I'm going out on a limb here, but I would argue that Plonk is one of the first ZK proof systems that was engineered instead of and not so much designed, as in it didn't come out of academia. It came out of a need to solve problems in industry, and so it's tailored to do that at the expense of perhaps losing a bit of how do I put this? Like, to give an example, like we don't use the R1CS abstraction layer for Plonk because we didn't consider it. It's not. We would argue it's not particularly efficient for the kind of algorithms you want to implement in the real world. What you really want is the ability to do weird things like elliptic curve point additions in a single constraint. You want to do very weird things like look up an 8-bit exclusive or perform 3 16-bit range checks and sum them all together. And so you have all these weird niche custom kind of mini circuit constraints that you can do very efficiently in Plonk because it's architected to do that. And as such, it's I would argue it's the most efficient ZK SNARK that exists for use in like for the typical algorithms that you use in kind of real world applications, and that's why we use it.
Shall I answer? So Zcash is actually used, or will have used by the time the NE5 upgrade activates, 3 proof systems. technically 4. I'll get onto that. So there's BCTV 14, which turned out to be unsound. There was Grot 16, which is sort of kind of the conservative choice at the time we picked it for sapling. And we're working on Halo now, so the next upgrade will use Halo. And Halo uses an arithmetization, which is essentially the same as Plonk, for exactly the reasons that Zach says. It's just more efficient to write circuits in that arithmetization. I personally think that it's the arithmetization that makes most of the difference, rather than the rest of the proof system. The other ZK proof system that's kind of hidden behind the covers is one that we used in the MPC. So we actually used the same framework that I'm sorry, I can't remember her name, was talking about before to convert a weakly secure MPC into a strongly secure MPC. So that technically is also a ZK proof system used there.
Daira, well, I guess maybe I'll just say, and then I want to ask you a question, Daira, if that's all right.
That's fine.
So we use a few different proof systems. We throughout development. First, we were using Grot 16, and then we switched to using. At some point, we're using the Groth-Mahler snark, I think, and then we switched to using Marlin, and then we switched to using our kind of Plonk-like snark, which we call Pickles, which is basically, which is kind of leads to what I wanted to ask you, Daira, which is what is Plonk beside, what are the other, you were like, oh, I think it's arithmetization that makes a difference, not the other parts of the proof system, but I'm just wondering, what are the other parts of the proof system in your mind, like the shuffle or which part? You know, it's very,
I consider the shuffle to be kind of part of the arithmetization. It's just, so Halo uses in a product argument instead of KZG. So that's.
Okay. Yeah. Okay.
So I guess it's
so
the cryptographic compiler mostly, although there are some differences in the IOP as well.
Yeah, I could give my I guess my 2 pence cents. So when we wrote the Plonk paper, the main thing that we were excited about was the arithmetization and the permutation arguments, basically being able to validate copy constraints between wires in a circuit, and a way of very efficiently representing arithmetic gates, such that kind of your polynomials very directly. There was a very direct mapping between kind of vectors of values that that belong to your gate wires and the polynomials that encoded them. On top of that, you need a polynomial commitment scheme to actually instantiate it into a proving system. And so we published it using KZG, but it can that can be swappable for other polynomial commitment schemes. And RL was quite keen on writing the papers to try and make it as commitment scheme agnostic as possible. But then obviously I think Plonk means it's become very much a piece of its own over the last 2 years, and so there's lots of teams have been adding to it and iterating and innovating. For example, Halo adds this a very efficient method of recursing between cycles of elliptic curves, which is kind of its own thing on top of Plonk. And then there's also the Pickle snark as well, which also implements recursion in a different way. And then we implement recursion in the third way, based off of various different requirements.
So yeah, actually the first version of Halo was based on Sonic rather than Plonk.
I also understand.
Yes, another proof system we've worked on.
I also understand that in this discussion we have Jordi, who said that he's using Grot 16. So I wonder, if you could give us your production angle on this and how come you're using this.
Yeah, I know that the Grot 16, of course, has some problems especially with trusted setup requirement, but the Grot 16 is still, at least from the gas. So if you are deploying something in Ethereum and you want to prove something, the verifier that's more efficient in Ethereum still is Groth 16. Plonk, I know that's getting very close to that, but it's still the best. So the best one is still Groth 16. Of course, Groth 16 has the other problems. Also, from the security perspective, Groth 16 is older. People from Zcash already has a lot of money there, so I would say that's more tested. It's more people know more than that. So when you are going to deploy something in production, something that you need to take in account also. And also the proving generation of the proof has been working for so the engineering part, doing computing proof fast and doing the algorithms, just writing a lot of code in assembly and just trying to get very efficient in what you're building. So maybe we are a little old in the new fancy set of protocols that are coming, that I think that they are great, and we probably will switch at some point of some of these protocols at some point, but we wanted to build something in production and reliable, and we got the tools also for Groth 16. So that's what, okay, let's do it in Groth 16 and let's push. Let's go as far as we can with this protocol. And I think it's not obsolete yet, Groth 16. I know that there is very good promising protocols, but Groth 16 is still there.
So I mean, I would say that the fact that say you have a security bug in your circuit and you suddenly have to do a new trusted setup, and you've got that huge attack surface of the MPC. Not just the fact that everyone can collude, because that's not really realistic in most cases, but there's still a huge attack surface to the MPC, even if you don't have everyone colluding. There's still a lot of code, and people don't check the transcripts. We tried to encourage people to check the transcripts, and they didn't. So it has been checked, but it's difficult to get lots of people to do that.
I agree, but at the end, you also have smart contracts there. So and a bug in the smart contract, it's also hard to upgrade. So yeah, I agree with you. It's of course, if you have a bug in the circuit, you need to run a trusted setup. So it's like, okay, what you need to run a trusted setup, and I have a bug in there. So well, you can have some. I would say you can do something because you have smart contracts on top of there, and you can build something there, maybe putting in some safe mode at some point if you have some security there. But yeah, I agree with you. This is a pain. It's doing a trusted setup. It's a pain in many reasons, for many reasons, and this is one of those, of course.
So having done the zoom in each protocol, I think it might be worth hearing maybe an overview comparison, let's say, across all. And I think that Pratyush might be a good choice for that, given that ArcWorks, formerly known as Zexy, the library, has implementation for most of the protocols, if I'm not mistaken.
So in ArcWorks, we do have a implementation of a number of proof systems. So Groth 16, Groth Malin 17, Malin. We don't have a Plonk implementation yet, but I think sort of at ArcWorks, it's a pretty R1CS focused stack, and sort of in my mind, that's one of the advantages. I mean, I know that R1CS you can't perhaps get as arithmetizations for computations that you care about, but I guess my question for the Plonk focused panelists is that so there's a lot of optimizations that happen, say within Pickles, within Halo 2, within what Aztec is deploying. And I'm with R1CS, it's easy to share these optimizations, right? It's just R1CS, right? So somebody implements it in some library, I can pull it into my library. And I'm wondering how easy how sort of easy it is to use optimizations at the arithmetization level from, let's say, Pickles into Halo 2, for example.
You certainly pay a cost in complexity with the more complex arithmetization. There's lots more degrees of freedom and optimization choices that you have to make relative to R1CS. But I think it's worth it. It's worth it if you have people who are experienced in optimization, probably because they've they've done lots of optimizations in R1CS to start with, then you can really get the number of rows in the.
It may be worth explaining,
quite a lot.
it may be worth saying explicitly why arithmetization in Plonk/Halo is like better or different from R1CS, and how is it different? Is it a matter of having more than 2 inputs and outputs? What are the details on this?
It's basically because in R1CS you have a fixed gate, which is really simple, which is just doing a multiplication of linear combinations, and that's all you can do in a gate. Whereas in Plonk, you can define gates that are tailored to your circuit, and that doesn't compromise the universality. So you can define different gates for different circuits, and you're still using the same SRS in the case of Plonk, or the same CRS in the case of Halo 2.
And is there any way to get these kinds of, let's say, higher level gates kind of like shoehorned in the R1CS type systems? Or is it?
I mean, you can always translate between R1CS and a Plonk style system, but you lose efficiency in either direction.
I think you can, if you modify your like your proof systems, like let's say you take Groth 16 and you modify the kinds of computation it's checking from R1CS to some other circuit, some other sort of, you add some additional gates, or same with Mullen, you can do that, and there probably will be differences in costs and again complexity of the protocol. Yeah, so basically, like in most proof systems, you have this information theoretic layer and you have the sort of cryptographic layer. The crypto part would probably remain the same across all of these things. The information theoretic, which is what the arithmetization is what would change. And then I guess you can't really call it R1CS still, because you have R1CS is just you have some matrices and you're multiplying some linear combinations like between the variable assignments and the matrix rows and so on. So it won't be R1CS at the moment, but you can imagine generalizations of R1CS, for example, with more matrices or more and like higher rarity multiplication gates, which might get you the same to some level of like parity with the sort of Plonk arithmetization. But
may I? Oh, go ahead, Pratyush. Sorry, I didn't mean to interrupt you.
No, sorry. I said it's like it wouldn't be, I guess, standard R1CS anymore.
I was just going to say, like, I wonder where exactly the question is coming from, because if it's about finding like a common, thing that embeds into R1CS and also into Plonk or whatever. I mean,
yeah, I think the motivation is just see if, like, with R1CS is like a shared format that a lot of proof systems can easily, like, you can go from Groth 16 to Mullen with like, no change in your circuit itself.
Well, I would actually push back. I would actually push back on that, because, there's R1CS in Groth 16 and there's R1CS in Marlin, and R1CS
different cost models. Yes.
Yeah, exactly. Yeah,
and
exactly.
Sonic is another variant. Yeah.
Yeah. So I maybe we're already more in the the world of incompatibilities, even just within Groth or within R1CS than.
Yeah, so there's like an efficiency difference, but I think like from the, like, if you're like a high level dev who just wants to use, who's just writing circuits, right?
Well, you could say the same of Plonk, right? I mean, you can imagine Plonk is just for R1CS also, and there's just an efficiency difference.
I think the advantages of Plonk are so compelling that we will work out the kinks and we will all converge on some sort of way of modeling it or describing it.
So I guess I was just wondering if there is such an effort already. Yeah, I was wondering if there's such an effort already and sort of what the feasibility of this would be. Or
right now, I don't think there really is a concerted effort, and it's because I think the fundamental problem, I think, is just the fact that ZK-SNARK proving systems across the board are slow, like incredibly slow. If you want to create a SNARK proof of a program, that construct that SNARK proof will it'll be like between 1 million and 10 million times slower than the actual program. And so if you actually, so when using this stuff that's taken in production, you want to do anything possible to speed things up. I mean, like, for example, take what we're doing at Aztec or what Jordi's doing. You want to construct relatively complicated ZK-SNARK proofs, like in a web browser using WebAssembly. you're really on like consumer grade devices like old laptops and phones. You're really at I think all of us have this problem. You're really at the bleeding edge of what's possible, and you can't afford to have an abstraction layer that simplifies circuit construction, proof construction at the cost of efficiency, even if you really want to. And so that's why right now, like we're all developing our own different like modifications to slightly different circuit administrations to eke out tiny little optimizations to make our circuits faster for the very specific use cases we have in mind for them. In a way, I think the landscape is a lot like to use an analogy, like 1980s home microcomputers, where every computer has its own unique bespoke architecture that's optimized for certain design constraints, and they all have their own machine language and means of programming them at a very low level. None of them share any kind of compatibilities with one another, because to do so requires creating an abstraction layer which adds an inefficiency which can't be tolerated because these devices are so computationally limited. And I think that's where we are at the moment. And I think over the years, as ZK-SNARK previous systems become more capable, like if we ever get into a world where practical succinct linear time previous systems turn up, or where like GPU accelerated proof construction becomes commonplace, or just if computing resources increase, then I think we're going to be in a world where there's enough overhead that you don't need to to optimize down to the bare bones, and you can afford an abstraction layer which unifies all these different proving systems and creates like a very nice an idiomatic way of defining circuits that doesn't actually depend on the underlying proving system. But I'm not entirely sure we're there yet, just because these proving systems are still very slow.
The little tidbit, and there was actually an attempt to standardize between home computers. It was called MSX, and it never went anywhere. Partly because, yeah, they didn't have enough memory. It was very difficult to pay the cost of that abstraction layer.
I think we will touch on standardization towards the end of this discussion, but personally, it feels that the tech is such at a very high iteration early stage, where any effort of standardization kind of very quickly gets beaten by somebody that just chooses to move very fast. So to be determined, in my opinion. Yeah.
No,
maybe
I think this is a totally solvable problem, though. I think we will converge.
Yeah, I agree with that.
I agree.
Something else to discuss would be around the trusted setup topic. So let me kind of phrase the questions in that way. Firstly, does having a trusted setup matter? Is it great if you can avoid the trusted setup at all? And does having a universal setup with a pair application setup, is that good enough? Because there's a nuance, let's say, among the three, and I think it's worth exploring, perhaps.
I mean, I'm completely biased here because Halo is no trusted setup, and we chose that. So partly because we saw how to do it without a trusted setup, and that actually makes the proof system much simpler. It means you don't have to use pairings, for example. I mean, it's not that pairings and trusted setup always go together, but they tend to. There are only a very few sort of useful, and there's one polynomial commitment scheme that uses pairings and is completely untrusted. So I made this point before, but I think the fact that you can make security fixes on a very tight turnaround means that so the per circuit trusted setup, I would say it's just completely obsolete, especially for applications like blockchains where doing upgrades is really difficult, and you have attackers who can get a lot of money if they exploit a bug quickly. But that doesn't choose between universal setup and untrusted.
I agree. Yeah, I agree with what Daira said, and we also our Snark uses an inner product argument, which is very similar to the one used in Halo. and so it also doesn't require a trusted setup. Yeah, I mean, I think it was useful not just for the reasons that Daira outlined, but also there is an advantage over having, well, there's sort of a few advantages over having universal setup. I mean, it mainly just comes down to avoiding having to do the bother of doing the setup. You know, that saves like a month of, you know, someone's time, basically.
I mean, we could actually have used, if we'd used pairings, then we could have reused the sapling setup for small enough circuits, because it's just powers of tau. But anyway.
Actually, that kind of reminds me, there's a really important practical aspect of avoiding the setup, which is you get to use smaller fields throughout the whole protocol.
Yep.
Because if you use, you know, the snarks that use setups are all ones that are using pairing friendly curves, and they're, you know, you're basing your whole protocol on some elliptic curve, which has to have a sort of larger than would otherwise be necessary field size. Which slows down all of the computations in the prover dramatically, because you know, the prover computation scales like quadratically or even cubically in the field size.
Yeah.
Sorry, carry on.
Sorry. So yeah, that's a very relevant point. So I think there's a trade-off that has to be made between a universal setup and no trusted setup at all. And that's whether you need succinctness, because all of the universal setups, at least when you're using elliptic curve-based snarks, they all come with the trade-off that the verified time is typically linear in the underlying circuit. And you can use Taylor star recursion so that it's linear, so that the circuit that your linear time in is small, but you still have that linear factor.
You can do it in square root. But
oh yeah,
I think that there will be completely interested setup snarks that have square root verification reasonably soon.
Yeah, I think you can.
I mean, if you count Spartan, then you already have that.
Yeah, I think you could. I mean, they're already untrusted polynomial equivalent schemes that have square root proof size and square root verified time.
I think the only reason why we don't have that in a deployed sort of system, so there's Dory and Spartan, but
well, I mean, like, I think, well, there's a paper in 2016 written co-authored by Jonathan Bootles, who's in the call. He maybe could talk about it. Yeah, but like, so you still have a trade-off where it's not polylogarithmic verification time, and you don't have polylogarithmic proof size. Now, whether that's important to you is a very relevant question, because if you're running your own layer one blockchain like Zcash or like Mina, then you can probably afford to run a linear time verifier, and you can afford to have a relatively large proof size, because if you're using rollups, then it's not a big deal.
Also, even if you have separate proofs, and the batch verification is really efficient. The constants for the batching is very small.
Also, isn't fractal count?
Fractal is succinct. It's completely large proof size, but yeah, I think sort of unfortunately the hash-based snarks, IOP hash-based snarks are, I guess they don't enter these kinds of discussions because the proof size is large. So for many sort of, you know, per transaction kind of applications, they don't make sense. But I feel like if you want succinct verification and transparency, it does exist. I mean, via Fractal and also via these quarks recently using the Dory polynomial commitment scheme.
If you need polylog proof size and polylog verified time, then you need a trusted setup. And so for us, for example, we want
but that's not you can. So the quarks, if you see in the chat, Fractal is, I mean, they're completely large proof size, but it's polylog proof size and verification, as well as if you look in the chat, Michele posted a link to quarks, which are also polylog proof size and polylog verification time. It's still like larger than
okay, so I'll take that back. But about the asymptotics, but the constants here also matter immensely.
Oh yeah,
and
it's all about the constants.
Yeah,
so
so
like,
it
for
depends on your
example,
application. So if your application is like, as I said, like per transaction, then it might not make sense. But if it's like, for a roll-up kind of thing, then it might make sense. It depends.
I guess what I was trying to get to is, if you want to build Ethereum, you don't really have an option. You need you can't really use any. I'm fairly confident that you can't use any of the existing transparent proving systems, because the gas costs to verify such a proof, either through the proof size or the verify time, would run you in the tens if not hundreds of millions of gas. So that's really constrained what we have available, and so that's one of the reasons why we put together Plonk, and it's universal set up in the theme of Sonic. And I think there's well, obviously I have skin in the game here, but I think that setups are good enough as long as you have large amount of community engagement. When you run the trusted setup, you have multiple implementations, you have the transcripts are verified, then I think that there's enough kind of community consensus for people to be comfortable using these. As I think we've seen, because we've deployed to mainnet. Matter Labs is also using our trusted setup, and no one has really it's not been a particular issue. Same with Zcash, at least with the sampling one, given the bug in the previous
said about
version.
BCTV brought in the better.
So I think it's good enough. I think having a transparent scheme is valuable, because you get peace of mind. You don't have to worry about the setup. You don't have to do it. But I think it's more of like a procedural annoyance than actually than something which will actually undermine or limit the adoption of the crypto system.
I mean, let's not underestimate procedural annoyances, because it takes a lot of mental bandwidth to be doing a setup at the same time as designing a new circuit and protocol.
But it doesn't if you want to use somebody else's setup.
That's true. Yeah.
Yeah, I think personally, like the improvement from going from per circuit trusted setup to universal setup is much larger than sort of the improvement from universal setup to transparent setup. I think the diff there is, I mean, it's still valuable, but I think it's personally much, it's not as large as the other diff.
Well, you have to factor in the efficiency due to using smaller curves. So if you use, let's say BN254 is roughly 102 bits of security. So if you don't think that 102 bits is enough, then you either have to go to
that's another
4 or 448, or sorry, I lost my train of thought. And if you do that, then you're paying, let's see, it's at least 2.25 times the field arithmetic for multiplications, maybe more for scalar multiplications. So you've got to compare that with the advantage of succinct verification. And if you have small enough circuits, then the smaller fields win.
Yeah, so I think it depends on the application. There's like a lot of trade-offs to be in the space. You're right.
I mean, Halo has a very low recursion threshold, and the recursion threshold is for Halo 2. I think it's less than 2048 rows. Don't quote me on that, but it's, yeah. And our circuit for Orchard to be used in the next Zcash upgrade is, oh no, I'm wrong. It's Orchard is 2048 rows, and the recursion threshold is less than 4096.
Cool. So maybe switching gears a bit, in like the whole blockchain industry, there's this whole quote about trust but verify, whereas we have like these papers and very long code, very big code bases, which potentially are not audited or peer-reviewed adequately. Daira had a good point around proofs of security maybe not being checked thoroughly, or that they're hard for engineers to implement. So I wonder what the group thinks around that. How do we improve this? Should we have a specification language? Can we auto-generate circuit code from that? And so on and so forth.
Yeah, so writing specifications in LaTeX is terrible. And you end up making quite a few mistakes. Audits are essential. I mean, audits will be essential anyway, but your audits are actually finding bugs. So yeah, if I could do everything in a proper specification language, then that would be wonderful.
Pratyush, since you're maintaining a large repository of implementations, I wonder what you think on all this.
Yeah, certainly think there's like a big open space for improving at basically every layer of the stack. You have, I don't know, probably formal verification at like the algebra level, so elliptic curves, field elements at the arithmetization level, for example, when you're talking about these polynomial IOPs, is maybe you can have a language which proves them, you know, it matches like whatever soundness property you need. And then above that, at the crypto layer, like with your polynomial commitments or something. And then above that, at the, you know, once you're actually writing your circuit, how do you prove that your circuit actually matches like a higher, like some higher level spec? I think there's room at every layer of the stack. And I think we're just sort of, because the field has become sort of more engineering oriented in the past couple of years, I think we're just going to start seeing more and more work in the space as more and more sort of money is on the line for these kinds of proof systems. But yeah, I wish it would come quicker.
But I would say, like, I wouldn't hold your breath, because like, yeah, someone, Georgios, I guess you pasted fiat crypto. It's like, how many years of using finite field arithmetic in production in cryptographic protocols, and like just now there's a formally verified implementation. You know what I mean? So it's like,
yeah.
I think there's a lot of space between a fully formally verified implementation and basically just writing Rust code and not having any extra tools. But there's a lot of space in between there. And I think there's scope for even just using libraries and frameworks. You can build things in a way that would be a lot easier to verify.
Oh, I
mean, you can take
100%
advantage
agree.
of the. Yeah, go ahead. Sorry.
I was just going to say 100% agree. And like, there's a reason that like we don't, write our whole circuit just gate by hand, and instead write it as a program.
Right.
Because it's easier in principle to machine verify, and it's easier in practice just to read it and kind of be confident and have invariants that are sort of locally enforced and so on. But
I mean, you need abstraction in writing circuits as much as you need abstraction in any kind of programming.
No, I agree. Sorry.
I can just share our experience. We write circuits in Circom, which is a language made for that. Of course, you need to audit Circom, and then you need to, it's like a lot of things, and it's hard. It's like we pay like 2 audits, and if I tell you the truth, I trust more the internal audits of the team and people that really understand what's going on, and just checking in there and forcing to check there and doing like double checks with other things that external audits that at the end they are checking there, but you don't even know how deep they went. So it's my experience is that it's hard, the auditing stuff, and at the end is just putting a lot of the best effort you can, and yeah, learning as you go.
Yeah, I mean, if you're paying a third-party auditing team, you're probably only paying them for a few weeks at most. So, how long do they have to get into the depths of the design decisions and whether everything fits together? I mean, they're keeping you honest. If they were to find serious problems, then you would probably think that there are also other problems that they didn't find. So it's valuable in that sense.
For us, for example, the best audit that we made is not really an audit, is we fully rewrote the CIRCOM in Rust, and there is a full team just writing that. And just having two independent versions of CIRCOM written, this gives so you need them to match one the other, and then it's when you really can you see a lot of things. And this is, for example, something that it gives me much more confidence that an external audit people just checking for a while your code.
Yeah, multiple implementation really works. We implement a lot of stuff in both Sage and Rust. And we cross-check them. And that's actually a relatively easy, low-cost thing to do, because you can write those implementations in parallel with different people if you have enough people. And then if they don't match, then one or the other is wrong.
I think it's just finding an alternative language to Rust or writing the alternative implementation.
So Sage is brilliant. So Sage is exactly what you need for doing number theory cryptography.
But even for like for example, the final snark, if you like.
No, we don't do an independent implementation of that. If we had enough time, then yeah, that would be good, but we don't.
Awesome.
So I think just
no, sorry, go on.
I don't want to say what you, but I think to summarize, it's a mess, isn't it? So it would be really nice to have more tools around writing circuits, specifying grouping systems. And just to mirror what people have been saying, I think there'll come a time when the ecosystem grows, when there's enough money on the line, when there's enough people who know how to do it, who are working in this space. Because right now, anybody capable of writing those tools is too busy and having too much fun writing their own circuits and grouping systems to write the tooling for it, which is a bit of a problem. So I think the ecosystem needs to grow substantially, I think, before these problems are really going to be solved in a scalable way.
And there are sort of language people and people who know programming language theory among the ZK community. We can do this. It's when we have enough time.
Awesome. So maybe moving on to the smart contracts part of the discussion. So for many people, smart contracts means like the kind of software that you write on top of Ethereum and you deploy to the Ethereum virtual machine and so on. But for this group, I guess that the smart contract is basically a circuit or an AIR or whatever. So I wonder, what does smart contracts in ZK mean for you? What is like the design space for them? Is it like something that uses like individual circuits which you kind of stitch together using recursion? Is it using a virtual machine? And so on. Do we need DSLs for coding the smart contract? So basically any kind of thought on that subject.
I would say there's kind of like two layers. Like one is like what happens off chain and then what happens on chain. So like on chain, you'll have some basically set of kind of dynamic behaviors that are permissible. They range from the very impoverished, which would be like in Zexy, where the only on-chain behavior that's possible is like add to the basically like add to the set of commitments, or check against the set of commitments, to the more rich. You could imagine a more rich set of permissible on-chain behaviors. Like in snaps, there's various things you can do, like kind of look at aspects of like the current protocol state. You can kind of you can sort of make assertions on like the state of other accounts and so on. Yeah, so that's kind of like the on-chain thing. And then there's like the off-chain thing of like, what are the kind of, in a sort of static-ish way, what are the kind of state transitions which are permissible? And basically there you're kind of doing a lot of the computation off-chain, and then just kind of having the proof on on chain and sort of stepping the state machine on chain, but like the computation that's involved in being able to step the state, like individual little state machines, is happening off chain. Maybe I didn't do such a good job of explaining, but okay, anyway.
Yeah, I think the key question there is if, what level of privacy is your goal. So for example, in Zachary, we went for a very strong guarantee that you want both functional privacy, which means you hide what contract is executing, and obviously data privacy, which means you hide what data is executing. Now, obviously, for many applications such as AMMs, you can't actually meaningfully achieve these guarantees like within the functionality of an AMM. So you have to relax it, and maybe you're okay with revealing, oh, an AMM is executing, and maybe this is like the total balance or something like that. But yeah, so I think the biggest question in sort of deciding your programming model and how you would actually, what kind of programs you can support is on what kind of privacy guarantees you want. If you don't want any privacy, then you can just pick up, let's say you write a zero knowledge VM, and you can just prove that's secure, and then that's fine. But if you it depends on as what kind of privacy guarantees you want to afford and what you are okay with sacrificing.
I mean, I completely agree. The programming model is the key thing. I'm not convinced that we even have a workable programming model for smart contracts in general, even disregarding privacy. I think if you look at the history of bugs in smart contracts on Ethereum, I think it's an unsolved problem how to write smart contracts that we have confidence that they're actually doing what is intended. And that's partly why Zcash has been sort of privacy first and then scaling and then programmability rather than any other order. Because these problems will be solved, but I'm just not convinced they're solved yet.
I guess I would partially disagree with you, because I agree in theory that it's not solved. There's no way of writing secure smart contract code. However, I think one of the values of the Ethereum smart contract programming language and Solidity is even though the design of the language is in hindsight not the best, you do it a different way if you was done it from scratch. But the protocol designers didn't know that at the time back in 2015. And despite the flaws in the architecture, the fact that it's been battle tested so heavily over the last 6 years, I think does add a lot of value in that that there have been hacks and there have been security breaches and there have been flaws, but through that kind of a shared experience, there is a kind of an Ethereum safety manual that's been, I guess you could say, is written in cache. The cache has been lost in all of these security breaches. So there is I think there is this kind of it's a long way away from being able to write provably correct code, but it's I think you can write smart contract code today and have reasonable security that is probably going to be okay.
I mean, the question is probably enough.
Pardon?
The question is what degree of confidence is enough, and I guess it depends on how much money you're writing on a given contract.
Yeah, exactly.
When they come, sorry, just in the interest of time, because we have just 10 minutes, it might help if you could kind of differentiate between the two schools of thought that exist right now with respect to, or maybe three schools of thought that exist with respect to building smart contracts, which is like the Zexy style UTXO powered by predicates model, the kind of thing that you are doing, Zach, where you have like a circuit and you bundle them all together. And then the virtual machine type thing that is very similar to Cairo by Starkware or Zinc by Zinc. Yeah.
I can try and give a summary. So yeah. What we're trying to do is it's very much influenced by Ethereum smart contracts, because we want smart contract developers to work on it. So we want to create a private smart contract ecosystem that has very familiar kind of semantics to Ethereum smart contracts. So you have traditional cool semantics. So Instead of predicates, you actually have a concept of a contract, which is a set of verification keys that define the various methods of that contract. And then you have kind of a Merkle tree of shared state across all contracts, but such that you still use your UTXO model, so you can't see which contract is owns which various state variable. And you use a similar concept, like the architecture borrows very heavily from Zachary. So you still have a concept of a kernel snark, basically a snark circuit which uses recursion to verify the correctness of a inner private transaction smart contract. Where we differ a little bit is that our architecture kind of implements a call stack. So the kernel snark will pop one circuit proof off the call stack, verify its correctness, and then based off of the public inputs from that circuit snark, it can then conditionally push one or more additional transactions onto the call stack. And then you basically run the recursive circuit over and over and over again until your call stack is empty. At least that's the general high-level idea, but it'll take a long, in the interest of time, I'll skip over how we achieved that because it's complicated. Then I guess when it comes to the ZKVM type architecture, it's the kind of thing that Metal Labs and Starkware are doing. That's a very different beast because it's not private. So their goal is basically to create a feature-rich equivalent to Ethereum smart contracts. So either through Cairo having its own programming language, which is Turing complete, or ZK Sync, which they're planning on apparently launching a EVM compatible ZK Snark virtual machine soon. So those architectures, you can't really have privacy with them because the circuits that these languages generate are absolutely massive. You need massive centralized computational resources to construct the proofs.
Zach, on this point specifically, so assuming that, let's say that privacy is not a direct goal of the protocol designer, and that's an assumption that I think, that might not vibe with everyone, but some people are okay with that. I wonder if you have any ballpark, or you can conceptualize maybe the constraint number and what this kind of would imply for the proving costs in terms of time, resources on the cloud, and so on.
So I can only really guess, make educated guesses, because I don't think Metal Labs or Starkware really publish low-level architectures or benchmarks. But I would estimate that you would need if you want like a one-to-one EVM, if you actually want a ZK Snark that verifies an EVM simulator, like one-to-one. So you have things like SHA-3, you have things like precompiles, which is probably not that realistic. Then your circuits could run into the hundreds of millions of constraints, if not billions.
Right, but let's say that you don't have the SHA. Take out all the outliers, like the things that create enormous amounts, and focus on the things that are like the memory model of the EVM and that kind of stuff.
I think even that is really inefficient compared to compiling to a specialized circuit. I mean, to me, the VM approach is just really suboptimal, and I'm not even sure why people are so keen on it. I don't think that you need to pay that cost in order to obtain the advantages of sort of having a rich compilation model. I think you can have sort of a rich source language and compile it down to Plonk constraints or whatever your proving system supports. And we might not have the tooling to do that yet, but it will easily beat a VM-based approach eventually.
I would just like to inject one thing, which is there's the distinction between the kind of, programming contract architecture that Zach was describing, and then this centralized proof architecture. But then the VM thing is actually a proof system technique. It has nothing to, it doesn't really exist on the same level of abstraction as these two architectures for smart contract systems. It's a proof system technique. You could apply it to Plonk type proof systems, yeah. Anyway.
Oh, yeah. Sorry, I completely glossed over that. Yeah, it's a proof system where the prover kind of has to commit to the description of the circuit that they're proving, and then you need to verify the correctness of this claim, which adds some overheads. That's not really the bottleneck with certainly you can create, I think, somewhat efficient VMs if you make them SNOC friendly or Stark friendly. The EVM is kind of it's a real unpleasant it's a fine architecture for what it is, but if you want to turn it into a snark circuit, it's very unpleasant. Obviously the designers know back then, because it's a 256-bit virtual machine, so every single opcoder performs 256-bit operations. The memory model is very unpleasant because it's byte addressable. So you have to implement some kind of RAM abstraction that can index individual bytes using field elements, which is a right pain. Then we've also got this parallel call data structure, and then you have to actually correctly implement call semantics. So you need to copy across call data from memory between different call frames. So it's very, very hard to do. I suspect you would need FPGA accelerated SNOC provers to really get the job done.
Cool, thank you. Unless anybody else has any input on this topic, I'd like to switch the discussion to standardization and hardware acceleration about the future.
And also maybe we can save some time for
absolutely. So the panel will last 10 more minutes, so we will have time for the questions.
Okay, good. Yeah. I think we should move on because you could talk about VMs and compilation all day.
Absolutely. So firstly, on standardization, I guess there's three angles. Firstly, there's the proof serialization format. Literally, how do you put your data on disk? How does it get loaded from other software? There's also fragmentation across libraries. There's Bellman, there's 10 forks of Bellman, there's ArcWorks and 10 forks of ArcWorks, or Zexy before it was called ArcWorks. And then there's Circom, and everything has like very different interfaces. The libraries that are in Rust have different traits and so on. So there's also that angle for to standardize. And finally, it seems to me that standardization is also important for recursion, because when we have 10 proofs which are generated by independently, parties that don't know each other, if it comes in a standardized format, maybe you can batch all of them together in one proof and verify it elsewhere and so on.
So I'm not sure that the latter is really a big problem, because as long as you have a format for a verification key, you're going to be able to verify any circuit regardless of where it came from. The problem is not on the verification side, it's mainly on the proving side.
Still, a verification circuit needs to know what format the proof will be in and what format the. It's probably not as much of a problem if you have a mono blockchain, just within a blockchain. So, for example, within Mina, it might not be a problem because it's one implementation and the format is consistent within the blockchain use case. But I guess once
the interoperability problems come because it's quite a complicated thing you're doing when you're proving. You've got to generate the witness as well as actually generate the constraints. And things like that, and how you compose gadgets are where the libraries differ or where the languages differ. Whereas on the verification side, you just need a verification key and the specification of the proof system, and you're done.
I guess my point is that the verification key format and the proof format also need to be compatible, right? Like if I have one.
There are plenty of things to specify, but it's such a simpler problem than the proving side that it's much easier.
So in Circom, so one of the big things is that in Circom, for example, we split very much what's the constraint system in one side and the witness generation in the other side. So at the end, Circom, what it is a language that you write in the same language and you get like two things. One thing is another program, can be a WASM program or a C++ program or even any other language program that actually generates a witness. So this is what generates. So Circum generates a program to generate the witness. This is something that is clear, and this is the thing, and then generates a R1CS or the constraint system or whatever it's on the other side. And splitting these things, I think it helps because, you know, at the end is if you have you can have a program that generates witness, and this program can be in C++, can be in Rust, can be in Golang, can be in any language in there. But the problem is that you need to specify what's the standard language, you know, what's the standard way of computing the witness, and this is probably the biggest the most difficult thing to standardize, because it's not a format, you know, it's a program. So how do you standardize that? And this is probably the biggest difficulty, because at the end, R1CS at the end is agreeing in one format, and that's it.
I think that the kind of the end goal, hard to achieve though, is to just have a single kind of way of defining your program, which you can use to derive both the witness and the constraints from, although that's hard to do. Yeah, I totally see why SACOM went the way of separating witness generation and constraint generation. I think for mainstream adoption, if you want like regular engineers, you don't know a lick of cryptography to write snark circuits or write programs that turn into snark circuits, I think you need to present a language which looks a lot and quacks a lot like existing high or low level languages, like something like Rust or JavaScript. But that's a long way away. I mean, even like because it doesn't like like, for example, I think CIRCOM is quite easily the most widely used snark programming language in the industry, correct if I'm mistaken, because of how easy to use it is, even though compared to something like a JavaScript program, like, please forgive me for saying this, it really isn't easy to use compared to, like, you know, normal programming. But what am I even trying to say? That, yeah, I think we've got a long way to go before we can create kind of intuitive abstraction layers to write snark circuits.
I would slightly push back on the idea that it has to look like conventional imperative languages, because I actually think that constraint-based languages and functional languages are much closer to how we actually want to write circuits. I mean, but when I write a circuit statement for Zcash, it's in this pseudo language, which is completely functional. And are actually relational to be more precise, and there's no imperative aspects to it at all. And I wouldn't use imperative constructs if I had them, because functional languages are much easier to audit and understand how the statement corresponds to the high-level protocol.
Great. So thank you. So for a final question on this, before we move on to the audience questions, what do people think about hardware acceleration? What kind of hardware will we see? Will it be ASICs, FPGAs, things that we don't know yet? And where are they most useful?
It seems cool to me, and but it's only, you know, where the speed really matters is, I think, on the individual like user who's trying to hide some private data, and less on like the roller upper. And
depends on how much data you are actually operating on.
I guess so, but like, it's, you know, in all the approximations I've done, like cloud CPU is just so cheap, you know, relative to the amount of data. So it doesn't seem to me to matter that much, but I mean, yeah. And so then it's like a little unclear to me, because it's like, you know, until there's like a whatever snark chip on iPhone or whatever, that, you know, then it's like, well, you know, you can just throw more cloud CPUs at it.
So if you're trying to process lots of data, as for example Filecoin is, or if you're trying to prove a VDF, you know, using the VDF construction that uses snarks, where the VDF is deliberately slow, and that gives you huge circuits, or huge IVC computations. So in that case, yeah, you definitely need some kind of hardware acceleration, preferably.
I feel
and
like
Filecoin is using GPUs already.
Yeah, I feel like an interesting direction on that front would be, I think what will end up happening is that probably you'll have proving hardware that lives in the cloud that you can access. And right now, I think there's like a dilemma. If I'm a smartphone user, how can I prove something privately? It's a large statement. I can't outsource it to the cloud because it's private, but I don't have the computational power locally to do it.
Right, but maybe the things that you need to prove privately only require fairly small circuits, and then you submit the proof of that part to some cloud prover that doesn't need to, where the proving system doesn't even need ZK. It's being used for scalability.
I think that's been the case for existing applications, but going back to like the smart contract discussion, I feel like once we sort of open up the, just bring ZK to the masses, I guess, but actually having people prove computations, not just like, it's like a Zcash circuit, but more like a full-on smart contract kind of thing. I think people want the more powerful proving infrastructure, and it'll be interesting to explore how that will come about. It'll come out via proof system improvements, but also that can only take you, I guess, so far, because there's still going to be some overhead with using proof systems. So it'll be interesting to see how you can leverage.
Go on.
I'd like to go out and speculate about what the future is going to look like, because I think that whilst hardware accelerated extraction is going to have a niche, for example, like the verifiable delay functions Daira mentioned, I don't think it's going to be the way this industry goes, because I think basically, I think that, well, I'm very biased here, but I think that one of the most valuable uses of ZK is privacy, which means that proving systems need to be fast enough for proofs to be constructed on local hardware constrained devices. This is again just speculation opinion. I don't think users will be willing to accept delegated proof construction if it requires leaking information or secrets to a third party, no matter how trusted. And this requirement is going to force proving systems to become more efficient. I mean, we've already seen that with over the last 3 years. We've had order of magnitude improvements in how fast smart proving systems are, and I think that's only going to change. That's not going to change. I think particularly the next threshold are linear time proving systems. I mean, there are already some interesting theoretical papers out. I think it's only a matter of time before they get translated into something which is practical for industry. And I think that what we're going to see is just a continual iteration and development of proving systems to the point where they're fast enough that you don't need hardware accelerated proof construction, even for rollup proofs, because now that we have efficient means of recursion, those are massively parallelizable. You can just spread the load across multiple devices, and as Izaak said, computation is cheap on the cloud. So that's the way I think it's going to go.
I think delegation protocols, but I think delegation protocols so far for proof generation are non-private, but I don't think that's the case forever. And particularly, I'm working on protocols to allow private delegation for arbitrary computations. So
just to,
but I mean, you can use a proving system that produces a large proof, but it has a very efficient prover, and then you can send that to someone to compress that proof into something smaller. And I think a lot of systems are going to use that approach.
Maybe, perhaps.
This is like maybe a good transition to the question by Mark around how recursion is viable in your different projects. So maybe based on what Zach said, recursion will be one of the most important things to have in a protocol, because it allows for massively parallelizing the proving stage. And seems like most of the group agrees.
I think if you want privacy, you need recursion. So I think for scalability, it's not strictly required. But if you want privacy or massively parallelizable proof construction, it's essential, because you need to be able to verify zero-knowledge proofs inside zero-knowledge proofs. And so for us, recursion is essential. I mean, that's like in 2019, I spent 6 months trying to get recursion, banging my head against the wall, trying to figure out a way of doing recursion on Ethereum with the limited pairing-based primitives. It opens up a massive space. Zexy wouldn't be possible without recursion. None of the advanced protocols that require like advanced call semantics or advanced privacy features are possible without recursion, and you can't really do effective compression. You can do a rollup without recursion, but if you want to do mass scale compression, i.e. rollups of rollups, then again you need recursion for that. So basically, it's I would say going into the future is going to be completely essential.
Yeah,
thank you.
And all proof systems will be measured on their ability to do recursion, unless they're for some specialized application.
Nice. Yeah. So maybe growth 16 is starting to fall behind. As a final question before we wrap this discussion by HR, what kind of primitive would you add on Ethereum today that enables zero knowledge proofs? And I guess this is maybe like more oriented towards Jordi and Zach.
There is one that's urgent to do, and it's the BLS 381. And this is because at least this is required at least for the Ethereum 2.0. See, I would say that this is, and for the security that Daira mentioned, that the current core that we are using is only 100 bits security. So this is, I would say, this is the minimum, and I'm sure this will be added very soon. But right now there is this EVM extension for working with 386 and 700 whatever, 756 or whatever a bit number of bits that should be able to write any primitive based on with this that should be quite cheap compared to that. And this is something that's I think is in the roadmap of Ethereum. They are working on that, and they will add, you never know when in Ethereum, but at some hard fork they will add something like that. With this, I think that you can do a lot of things with that. And I don't know, Zach, maybe you have others.
No, I mean, I think similarly, it'd be nice to have BLS 301. It'd be really nice to have BLS 377. Also, sorry, I just want to just add on the last question, because regarding recursion, I just want to apologize if it felt like we were ganging up on Jordi when it regards to recursion. I just want to apologize that that's not the case. Just want to say that I think what you guys have done with Hermez is incredible. Anyway, I just wanted to put that out there. But regarding primitives, yeah, like I mean, I would I'd probably like pay blood to get a Halo type verifier on Ethereum or a multi-scalar multiplication, but it's not going to happen, to be frank, because one of the strengths of the Ethereum ecosystem is the fact that it's decentralized, but it also is it makes it slow to adopt advanced primitives, because right now, like there are multiple Ethereum clients. There's one in C++, there's one in Rust, there's one in Python, there's one in JavaScript, there's one in Golang. And if you want to add native support for an advanced cryptographic primitive like multi-scale multiplication or Halo verifier, all these different projects have to independently implement them. And none of these projects really have in-house cryptographic expertise, because that's not what they do. And so you've got to go to basically a bunch of disparate decentralized teams and go, hey, you want to implement this bleeding edge cryptography that you yourself can't verify is correct? And the answer to that is universally, God no. We're never doing that. So I think also it would be nice to have things like Halo style verification or like generic multi-scalar multiplication over arbitrary curves. I don't think that's practical. I think probably the best we can hope for is BLS type curves being added in the near future.
Perfect. Nice.
Yeah, I mean,
sorry,
it's very frustrating that we don't have arbitrary curves, and that's what everyone wants.
The arbitrary curve ZIP is somewhat stalled at this point, but it might be worth rekindling the effort on that. In any case, I think we're a bit over time, so thank you, Daniel, and everybody else for your patience. Thank you all for this very vibrant discussion, and I look forward to seeing everyone again.
Thanks, everyone.
Thank you.
Matthias, we didn't get to your question, but I think it's a very good question. So I don't know, if you're interested, let's talk about it. But okay, bye.
Thank you so much to all the panelists. Seriously,
it was a lot of fun.
And to Georgios for such a good moderation. If you are interested in continuing some of these discussions, I am sure throughout the workshop we will probably touch upon some of these topics again. Hopefully, not all, but many of them. So make sure to join. Just two quick announcements before we break off. One is, don't forget to join on Monday. We're going to have two very cool parallel things going on. One of them is actually Pratyush is going to be leading a tutorial on zero knowledge proofs based on Artworks, how to implement applications and circuits. And the other one is going to be writing and expanding on the zero knowledge, the ZK proof community reference. So that's where a lot of these topics actually come in, to make sure that there is a proper reference for existing technology and solutions, right? So make sure to come, and we hope to see you there. And right now I'm sharing on the chat, once again, the link and the password to join the ZK job fair. It's a job fair for anybody who's looking for a job, but it's a networking and coffee event for anybody who just wants to hang out. So make sure to use Chrome and Firefox to join, and we'll see you there hopefully in a few minutes. Thank you again, everybody, for this great session today, and have a great weekend, everyone.
Bye, everyone.
Bye.
It's been fun. Bye.
Yeah, I'm happy to hear.
Bye, everyone.